Alright, so I messed up on the last video. I actually didn't do 29 or 30 somehow. So I'm throwing 29, 30 here at the beginning of this video. Um, so these last two questions are actually from problem set 1 before we get into problem set 2. 29 said you have 50 milliliters of 0.5 molar HCl. It's mixed with 50 milliliters of 0.28 HCl. Calculate the molarity of the resulting mixture. There's two ways to approach this. The way I've got it shown here is more of a weighted average, where you're dividing by the total volume, and you're kind of averaging the two together. What's really happening here is you do volume times molarity, moles, plus volume times molarity, moles. Moles plus moles is total moles. Total moles divided by total volume equals the molarity. Okay? So you're just kind of averaging them together by dividing by the total volume. And then in 30, you're supposed to show how the ionic compound would split apart, lithium chloride, and how the water molecules would be oriented around it, with oxygens from the water facing the cation and hydrogens from the water facing the anion. And that was the two questions I skipped. Okay, so speaking of things you need to apologize about, question 1 here. There is a typo in the answers. None of the answers are correct. That is a huge faux pas. This value here should have been a 14, but I accidentally hit the minus sign. So that should have been 5.0 times 10 to the 14th seconds to the negative 1. And now that we have the right answer in there, when we do the math, we're going to be able to find the right answer. But I kind of botched that. Sorry about that. When I was typing up the questions, I just hit a negative sign there. So it says, which of the following is closest to the frequency of light with a photon of energy? So we're looking for this equation here. This is Planck's equation, E equals h nu. We have the energy in joules, and Planck's constant is in joules. So we'll be solving for the frequency, which is in per seconds. It's photons per second, but we don't usually say that. So, and Planck's constant is joules per photon, joule seconds per photon. We don't usually say that either. So, anyway, we have the frequency, which is right there, which would have corresponded nicely to this answer had I not typed it incorrectly. And then, using the wavelength from the previous question, what color of light would that be? Well, let me turn my camera off here so you can see. Here we go. And we have the speed of light equation. Plugged in the speed of light. We plugged in the frequency. That gives us the wavelength. Unfortunately, it's in meters. And all of our choices on this chart are in nanometers. So we multiply by 10 to the 9th to get it to nanometers. And that looks like it's going to land in the orange zone there, right there in the orange zone. So that was orange. Cool. Okay, number 3. This one and a couple more are going to deal with our knowledge of energy, different electromagnetic spectrum and how they impact molecules, whether they vibrate, spin around, change electron energy levels, or just break apart. So let's do those in order from the least amount of energy to the highest. The least amount of energy is spin around, okay? Then the next most amount of energy is where they vibrate, where the molecules vibrate, where the bonds between them vibrate. And then the third most amount of energy is where the electrons actually change energy levels, so they go up to a higher energy level, come back down. And then the highest amount of energy is where the molecules take so much energy that the bonds actually break and shatter. So infrared is the second energy level. It's the one that causes them to vibrate back and forth, which is why the answer is B. Let's just adjust the other questions so that they would have been true, like kind of fix the true to false. So in A, if this part here says different electron electronic energy states, that's really for UV or visible light. UV or visible light would have caused that, not infrared. So that's why A is wrong, because if it had said UV or visible light, there we go. Then C, let's see, infrared photons, rotational states. No, rotationals, when causing that rotation, that's microwave energy causes things to rotation. So microwave frequencies or wavelengths cause that. And then the last one, chemical bonds can be completely broken. Completely broken, that is like X-ray or gamma. That's the real high end. This question's very similar. What happens in the microwave region? The microwave region causes molecules to rotate. Yay! Let's see, microwave photons. No, what is the electronic energy state change one? That is UV or visible. Vibrational energy, that is infrared. We have rotational energy. Oh, there's the second half of that sentence is wrong. I was having to read it. It says that infrared causes electron states, which is not true. Yeah. This has got two parts also. Infrared photons cause molecules to increase their vibrational state. So that's got A is the right answer. It's got the microwaves cause rotation, infrared causes vibration. Good. Number 5, N2 absorbs ultraviolet but not visible light. I absorbs both. Which of the following? So visible light does not produce transitions in the electron energy levels in N2. Visible light is caused by those electrons changing between energy levels. And so we can't see N2, but we can see I2. So here we go. A student uses a visible spectrophotometer to determine a COCl2 solution, produces the set known, and determines that they're going to use 510 nanometers to construct the standard curve. The wavelength corresponds to what wavelength? A wavelength of 510 corresponds to a frequency. What is the approximate energy? So if you have frequency and you're solving for energy, that's just E equals h nu. I didn't write that in there, but that's the energy equals h nu equation. Planck's constant gets plugged in for h, plug the frequency in for nu, and you get the energy. Hopefully I didn't have a typo that time. Number 7, a beta-carotene is an organic compound with an orange color. The diagram above shows the ultraviolet spectrum for beta-carotene. Which of the following statements is true about the absorption bands for the spectrum? So it's part C. The two main absorption bands are associated with transitions in electronic energy levels. If it's ultraviolet, ultraviolet is electronic. The other ones have other things that are wrong with them. And I just went ahead and highlighted the color coding, like ultraviolet causes electron transition, so that's why D is a good choice. Oh no, B could have also been a choice. Infrared causes, that's region Y, molecular vibrations. There we go. And then the microwave causes the rotation. So I highlighted why and how they match up. Number 9, there is an issue with the question on your paper. You might not see that, or that, or that, or that, or that. Like all of these things that are pretty important to the question somehow did not appear. I apologize. So what we have here is a calibration line where you have a set of different molarities that are known. They're put down into a machine, and the machine tells you how much light is absorbed. And so then with that calibration line, with these 5 points, they make a line. and then they can test an unknown. And in A, the student measures the absorbance of the unknown at 0.13. So I drew a line at 0.13, bing, hit the calibration line and came down, and it looks like it's halfway between 0.10 and 0.20, so I said it was 0.15 molar. B, calculate the moles in there. Well, you have 0.15 molar and you have 100 milliliters or 0.1 liters. That's 0.015 moles. In addition to the moles of copper sulfate from part B, what other quantity needs to be known to measure the mass percentage? We need to know the mass of the solid. See, they've got this unknown solid and a bunch of its copper sulfate. In order to figure out the total, all the percentages, they need to know how much the copper sulfate was and how much the unknown was. And then I drew the standard water molecule around an ion in there. Number 10, and also known as the final slide. The first one's a chromatography question where the pigment is put on the paper right here. See that paper right there? There's the pigment. And then the hexane climbs up the paper, and as it climbs up the paper, it separates the pigment in two different colors. See, this is T0 and the other one is T30 minutes later. They do tell you some important stuff. They tell you that the paper is polar, and they tell you the solvent down here is hexane, which I've added right below hexane is nonpolar. So as the hexane climbs up the paper, it drags the two pieces of the pigment out. And X has gone pretty far, so X is probably nonpolar because it's moving right along with the liquid. Whereas the paper is polar, so Y is probably polar because it's not moving very far. And then number 11, this word distillate throws a lot of kids off. When you're distilling liquid, you have a mixture of two things. And they're getting boiled, and then they get condensed back down somewhere else. And let's see, this part here is usually cold, and then they drip out the other side into a container. There we go. That's quite possibly the worst I've ever drawn. Oh, this has a fire underneath. There's fire. So you're heating the mixture of purple and red spaghetti. Let's call them butyl and ethyl acetate. And one of them is going to boil first, or vaporize first, and that's really going to be the one that's easier to break apart. So whichever one has weaker intermolecular forces will break off first. So, and then it'll go up as a gas. It'll go through that cold zone with the blue squiggly, and then drip down and be clean. And this drip zone here, that is the distillate. It has been distilled. So which one of those two would be in a greater quantity in the distillate? Well, if we look at the left side of these molecules, the left side is identical, so we can eliminate that from our conversation of intermolecular forces. They're going to have the same forces from the left side. Which one's going to have stronger forces from the right side? The right side would contribute London dispersion forces for both of them. But the bottom one would have more London dispersion forces because it's longer. Because it has more London dispersion forces, it wouldn't be as much in the distillate. It would be harder to break apart. So the answer is the ethyl acetate would be in a higher concentration in the distillate because it's a shorter carbon chain with weaker forces. And that, ladies and gentlemen, is the second problem set. Yay!